Salutations, everyone. Dr. Watson here. Welcome to 5-minute lectures by the Wiki channel. Today, I'll be diving into the fascinating world of general relativity, one of the pillars of modern physics. His theory, proposed by Albert Einstein in 1915, fundamentally changed our understanding of space, time, and gravity. But before we dive into general relativity, let's lay the foundation. You may have heard of Isaac Newton's laws of motion, which describe how objects move and interact with one another. However, as we learned more about the universe, we realized that these laws break down when objects are moving at high speeds or under strong gravitational forces. Enter general relativity, which offers a new framework for understanding gravity. Rather than treating gravity as a force between two objects, as Newton did, Einstein saw it as the curvature of space-time caused by massive objects. This means that instead of being pulled towards a massive object, objects in its presence are actually following the shortest path through curved space-time. Let me give you an analogy to help illustrate this idea. Imagine a heavy bowling ball placed on a trampoline. The ball would cause the fabric to curve, creating a depression in the trampoline. If you were to roll a smaller ball near the heavier one, the smaller ball would roll towards the depression, as if it were being pulled by gravity. This is similar to how general relativity describes gravity. Massive objects cause space-time to curve, and other objects moving near them follow the curved path as if they are being pulled by gravity. This theory has been confirmed by numerous experiments and observations, including the famous 1919 solar eclipse measurement that showed light bending around the sun as predicted by general relativity. So far, general relativity has been a very successful theory, but it's not without its challenges. It's incompatible with quantum mechanics, the other pillar of modern physics, which describes the behavior of particles on a very small scale. So, we're left with a question. How do we reconcile general relativity and quantum mechanics into a single theory that describes all of reality? This is the central question in physics today, and it's one that we're still trying to answer. According to the theory, the presence of mass and energy cause space-time to curve, and this curvature is what we experience as gravity. This means that objects in motion will move on a curved path as if they are being pulled by a massive object, like a planet. One of the key predictions of general relativity is the existence of black holes. A black hole is a region of space-time where the curvature is so strong that not even light can escape. This is because the mass of a black hole is concentrated in a single point known as the singularity. When a massive star reaches the end of its life, it can collapse into a black hole, with its mass and energy causing an enormous amount of curvature in space-time. One of the most famous predictions of general relativity is the bending of light by gravity. When light passes near a massive object like a star, its path is curved, as if it's being pulled by the object's gravity. This effect was confirmed by observations of stars during a solar eclipse, which showed that their light was bent by the sun's gravity. So now that we understand the basics of general relativity, let's dive a little deeper into the science behind it. One of the most important aspects of general relativity is its ability to describe the behavior of gravity. According to the theory, massive objects like stars and planets cause a curvature in space-time, which in turn causes objects to move in a particular way. This curvature is what we experience as the force of gravity, but general relativity doesn't just describe gravity. It also predicts some of the most strange and fascinating phenomena in the universe. For example, general relativity predicts the existence of black holes, which are regions of space-time where the gravitational pull is so strong that not even light can escape. The theory also predicts the phenomenon of gravitational lensing, where light from distant objects is bent by the gravity of massive objects along its path, causing the objects to appear distorted or magnified. Another important aspect of general relativity is that it incorporates the concept of time into the fabric of space-time. According to the theory, time is not a universal constant, but rather it can vary from place to place and from moment to moment based on the presence of masses and energy. This idea has profound implications for our understanding of the universe, and it has been confirmed by a number of experiments over the years. So, there you have it. General relativity is a fascinating and complex theory, but with a little effort it's possible to understand the basics and appreciate its significance. Of course, there is much more to learn about general relativity, and we'll be exploring some of these more advanced concepts in future videos. So stay tuned and subscribe to the Wiki channel, and as always, keep exploring and keep learning.